Today, what we're going to do, I gave you your assignment last week. Forgive me, but my copy is a copy of the one that the other group had, so my dates are different. But you were issued with that last week. Like I said, there weren't a lot you could do. What I'm going to do today is have a look at an example around part C of the first task, using graph plot and software. Plot the points, explore the functions of the model that might fit. So around how you can try and find a function that approximates to a set of experimental data. Because that's what you've got there. You've got some experimental data. So if you know how to integrate that using Simpson's rule and trapezoidal rule, so you could do that part of the assignment. But you could also try and fit a function of a kind of shape that's similar to that you get with a plotted graph, and come up with a function that you can integrate mathematically. Is the idea. The idea here is you're going to analyze this data in a number of ways and compare the methods. Okay. Now, I still have an issue with the autograph software. It's not saying we got a license, and IT is still working on that. So we're going to look at an alternative today, and hopefully I might even be able to get it for this afternoon. Very desperately need it to be available to us next week, because next week you're going to have the opportunity to finish off what you don't get done with regard to the use of software on the assignments next week. Okay, so these next 2 weeks are kind of dedicated to getting this work done, and the work on the assignment that you can only do here. You can actually, and I think I did put the link in, you can get a student copy of Autograph anyway. It's about me kind of showing you or giving you an examples of what I want you to do with it. And I can't do that at the moment because the board copy of the software is not working. But we will get round it, and I promise whatever happens, you won't be disadvantaged against the students in the other group if we can't get the software working. Okay, so the bits that you can't do will be not marked, and you won't be disadvantaged. So I hope everybody's okay with that. Yeah. So what we're going to do this morning then is I'm going to have a look at that part. This afternoon, what we'll do is have a look at. You should be okay with the numerical methods, bisection and Newton-Raphson's method, because we done that last week. There's really no more to do there, so that task can be done. Task 3, stresses on the bracket. I'll get you started on that in this afternoon session. Yeah. So this morning is this fitting a curve to this data, and I've on your handouts I've given you you've got some data that's of a similar nature, slightly different, but I'm going to talk you through how you might consider fitting that a function to that data. So go on to the slide on the board. We've looked at kind of a number of functions throughout the course that have uses in engineering. Linear, for example. Y is equal to mx plus k. I'm going to use, throughout these, I'm going to use k as a constant that would give you a shift up and down the y-axis. So it would give you, the constant is always going to give you the value, really, of the function when x is 0. So that will give you, if you were trying to fit a piece of data that didn't cross the y-axis at x equals 0, you'd be able to shift that function up and down the y-axis. I'm going to use that for k on all of these. Quadratic. So you might be able to fit it to a quadratic function of the form ax plus bx, ax squared, sorry, plus bx, plus again the constant on the end. cubic. Y is ax cubed, bx squared, cx plus a constant. Sine wave, y is equal to sine ax plus b, so that's frequency, phase shift is b, and a plus k on the end if needed to shift up and down the y-axis. Cosine, similar form. Always known that the cosine is 90 degrees or pi over 2 radians out of phase with sine. Yeah, so you got that ability, and we'll talk a little bit about that. But knowing what these shapes of these graphs look like is handy, so that you can say, understand, and oh, that looks a little bit like a sine wave. Can I get a sine wave to fit? That's what we're looking at here. Yeah. And then with those two, what's the main thing you're looking for in terms of those two, sine and cosine? Anyone? You're looking for something that's repeating and cyclic, aren't you? That's got some kind of wave shape to it. It's gonna, even if it looks like it's gonna repeat, you might not even got a full sine wave cycle, but does it look like it could be a repeating waveform for those two? Exponential. Yeah. You might also come across the exponential rise to a limit that you see with capacitors, for instance. Not got room for that one on the board, but you might. I'll put that one down the bottom. Y is equal to I 1 minus E to the KT, something like that. Yeah. So you could have that kind of shape that we got when we were charging our capacitors in first year science. It looks like that, exponential rise to a limit, for instance. You might want to try to fit to that. Logarithmic, y is equal to ln x plus k. Remember that k can either be positive or negative, depending on whether you want to shift up or down. So there are some functions that might be useful if you was trying to fit some experimental data to a particular function and get a close representation. What there then is for you to kind of work with the constants in there, because you might even have a constant in here actually, ln ax, ie to the x. That will change the shape or the steepness or otherwise of the curve that you get with those functions. Alright, so a knowledge of those functions, what they look like, or if not a quick graph of them, will give you an idea what shape they are and do they fit your data. So for instance, what I'm going to do, and it says here, actually, to the please. Tape. Every 2 seconds. with fly. Look. And do frequency. How can we get frequency? X on this software because we ain't got t as a not independent variable. All right, but for x, read t because our x-axis is time. How can we relate that? How can we get a value? Remember what this bx is here in terms of a function, a sine wave function. It is omega t. So how can I get that out of this function here, out of the data that I've got? What can I find from the data about that function if I want to make a sine function fit that shape? What can I get from the data? Anyway, think of the things, the maximum, minimum, is that related to the time frame? And park that for a minute. We'll need maximum and minimum shortly. Alright? But someone said we're going to go for frequency first, so that we'll go for frequency first. It doesn't matter which one you go for first. So what data can we get about what's frequency measured? Hertz in terms of cycles per second. What other quantity is related to hertz? Think about time. The period of the waveform. If we know the period, remember, frequency and period are reciprocals of each other. Frequency is one of period. Frequency is what period is one for the frequency. So if we can find the period from our data, an estimate of, we can find the frequency in hertz, and if we know the frequency in hertz, we can find it in terms of omega, can't we? Because we know that omega is equal to the frequency. So there's a way into this period of that data. Find the period. What is the period? One complete waveform. Have we got a whole complete waveform? But what have we got? Half. An estimate. But we've got the period, haven't we? Yeah. Are we going to estimate? Where's about half one? Kind of balanced around that point there, isn't it? If we were looking for a midpoint, that'd be here. Do you agree with that? Where would you say is half of that period? Somewhere around about here, or about 16, 18. It's only an estimate at this stage. You can always tweak it. Yeah, 18 seconds. So we got a period that is 36 seconds. Period from data. Period is approximately equal to, yeah, frequency is one of the period. What is less, I think, rather 1/3 a minute. Okay. Omega is 2 pi times the frequency. Yeah. So omega must equal 2 pi times 1 36. Yeah, because that's equal to pi over 18 and from the data P. Pi. Rating. What we got now? For two significant figures. 3.9, take away 0.16, 1.37, so 1.4. What did you say, sorry? On A, 1.4, there or thereabouts. Either any phase shift and develop in line. You can Add the amplitude to the lowest value, yeah. (1.6 to 2 significant figures, yeah. Right, we're getting somewhere now. We're quite close fitting this function to this data. It's looking like that might be a little tad high at the moment, but we can always adjust that if and when we can get it in line. So, lastly, how can we deal with the phase shift? Is the red line, the function line, currently leading or lagging the data in terms of time? Everyone agree, leading? Think about what leading means. It means the function peaks before what you're comparing it with. It's lagging. It's after. Yeah. So we need to add a positive phase shift to shift it left in terms of the graph. I can use the on here to show that. We need to go that way. I'm not going to find out what it is that way. That's what we need to do. Yeah. We could put a -1 in and shift it the other way, but we'd have to put one bigger than 180 degrees in to do that. There's no real point in doing that. So you always try and go the right way. Yeah. In terms of it. So end up with a phase angle less than 90 degrees where possible. All right, or certainly less than 180 degrees or pi radians. Yeah? So how can we find out what the phase shift is? We know what a full cycle is in terms of pi, don't we? A full waveform is pi over 18. So how can we express the phase shift in terms of that? One waveform takes 36 seconds. How can we find out how much time the function currently is behind the data? Where they peak, yeah. So we could look here and here in terms of time, and we could use those two, should get the same result. So there's a negative peak here at 10 seconds, and there's a negative peak here at 18 seconds, let's say. So we've got an 8-second difference. Yeah. So and the whole waveform takes 36 seconds. So, is not the phase shift 8 over 36? Let's try it, shall we? And that want to be, we've already said I want to be minus, didn't we? No, plus 8 over 36. I've gone wrong. Gone wrong somewhere. Must be minus 8 over. The whole waveform takes 36 seconds. Yeah? And the red line is 8 seconds behind the data. So it's 8/36 behind it in my opinion. So why ain't this working? Ah. Got a pi in there. You've got to have that in terms of pi. Sorry? Yeah. Let's try. Anything else we can do to that for best fit? Not against that adding 0.1, taking 0.1 away just to find the closest fit at the end, but I want to see you create initial estimates mathematically like we've done. Yeah? Shows you understand that function and how it might fit. So how could we make that perhaps a little bit better fit? What we haven't got is the option to go by 5, then going away from the 2 in the first. One. Yeah. And that. To the so I wouldn't fit with because you're difficult to make fine adjustments with low. So I will return to the assignment and kind of okay. Two part two. Now you're probably looking at the wrong function between and not, because you're effectively, if you switched 90 degrees, you're just one for that. I'm sure you. So I'm going to give you for the session, we will SolidWorks to do the bracket